Hello friends. Welcome to our channel Civil Engineering Infrastructure. I am your name and today we are going to discuss one of the most important topics in road construction in India, IRC 37-2018, that is, Guidelines for Design of Flexible Pavements. Whenever we construct a road, the first questions that come to mind are: how thick should the pavement be? What materials should be used? How many years will it last? All these questions are answered by this code IRC 37-2018. This is the latest revision released in 2018, which completely replaced the old 2001 method. Now, we design roads using a scientific approach with the help of software. In this video, we will understand everything in 20 slides, from basic to advanced, step by step, in very simple language. So let's begin. And yes, if you haven't subscribed to our channel Civil Engineering Infrastructure yet, please do subscribe, because we regularly bring you such technical gems. Friends, first let us understand where and when this code is used. First condition: this code is applicable only for flexible pavements, that is, roads constructed using bituminous materials such as tar or asphalt, which are flexible in nature and can bend slightly under load. It is not applicable for rigid concrete roads. For those, we use IRC 58. Second condition: this code should be used only when the design traffic is more than 2 MSA, where MSA means million standard axles. If the traffic is less than 2 MSA, then IRC SP 72-2015 should be used instead. Third important point: this code is meant for new pavements. If you need to provide an overlay or repair an existing road, then IRC 81 is used, not this code. Fourth point: this code is not applicable to flyovers, bridges, or overhead structures. It is meant only for road pavements. So remember, new flexible road, traffic greater than 2 MSA, and scientific design required, then IRC 37-2018 is your best friend. Friends, how are you finding the content so far? If you are enjoying it, please like the video and subscribe to our channel Civil Engineering Infrastructure. Also, don't forget to press the bell icon so you receive notifications of every new technical video. Let's move ahead. Now let us understand how roads fail. Friends, in flexible pavements there are mainly two types of failures, and our entire design process aims to control these two. First, rutting, that is, wheel path depressions. When heavy trucks repeatedly pass over the same location, a permanent depression forms on the road surface, creating grooves along the wheel paths. This mainly happens due to weakness in the subgrade. To control rutting, we check the vertical compressive strain, meaning how much compression is occurring at the top of the subgrade. Second, fatigue cracking, cracks caused by repeated loading. When bituminous layers bend again and again under traffic loads, cracks start developing. These cracks often look like alligator skin, so they are also called alligator cracking. To control fatigue cracking, we check the horizontal tensile strain, that is, the amount of tensile stress at the bottom of the bituminous layer. So, pavement design essentially means keeping both of these strains within their allowable limits. Now let's move to the science behind it. On which theory is IRC 37-2018 based? It is based on the multilayer elastic theory. Friends, we consider the entire pavement as a multilayer elastic system. At the bottom is the subgrade, which is assumed to be semi-infinite, meaning it extends infinitely in the downward direction but has a defined surface at the top. Above that are the granular layers, such as GSB, granular subbase, and WMM, wet mix macadam. These layers are considered infinite in the horizontal direction but finite in the vertical direction. On the top are the bituminous layers, DBM and BC. These are assumed to behave as linear elastic materials. Each layer has three main properties. Elastic modulus, E, representing stiffness, measured in MPa. Poisson's ratio, mu, usually 0.35 for granular layers and 0.25 to 0.35 for bituminous layers. Thickness, H, measured in millimeters. Most importantly, we analyze to critical locations. Top of subgrade vertical compressive strain, epsilon Z, for rutting control. Bottom of bituminous layer, horizontal tensile strain, epsilon T, for fatigue control. Friends, so far we have understood the basics, failures, and the underlying theory. Now we will move towards calculations. If you are finding this video helpful, please share it with your civil engineering friends and subscribe to our channel Civil Engineering Infrastructure so that we can continue bringing you even better content. Let's continue. Now let us understand the design criteria and reliability levels. Friends, we have two control parameters. Vertical compressive strain, epsilon Z, at the top of the subgrade. This controls rutting. Horizontal tensile strain, epsilon T, at the bottom of the bituminous layer. This controls fatigue cracking. Now let's talk about reliability, which means how confident we are that the pavement will perform for its full design life. In IRC 37-2018, there are two reliability levels. 90% reliability, used for national highways and expressways. This means there is 90% confidence that the road will perform satisfactorily for 15 to 20 years. 80% reliability, used for state highways and major district roads. The design life of bituminous pavements is typically 15 to 20 years, and it depends on the cumulative standard axles, MSA, meaning the total number of standard truck load repetitions expected over the design period. Now comes the most important calculation: how to determine design traffic. The formula is N is equal to 365 times 1 plus R, N1, R times A times D times F, where N is equal to cumulative standard axles in MSA, million standard axles. A is equal to initial traffic in the year of completion, in CVPD, commercial vehicles per day. R is equal to annual growth rate, in decimal form. For example, 5% is equal to 0.05. N is equal to design life in years, typically 15 to 20 years. D is equal to lane distribution factor. F is equal to vehicle damage factor, VDF. Now, what is the lane distribution factor, D? It represents how much of the total traffic is expected to move in a particular design lane. Typical values: single carriageway to lane 0.75. Dual carriageway to lanes per direction 0.75. Dual carriageway 3 lanes per direction 0.60. Dual carriageway 4 lanes per direction 0.45. Dual carriageway 6 lanes per direction 0.40. Example: if there are 2000 trucks per day on a 4-lane highway, then the traffic in one design direction will be 2000 times 0.45 is equal to 900 trucks per day. Friends, are the calculations clear? These concepts are very useful on site when you are doing highway estimation. If you want more practical knowledge, make sure to subscribe to our channel Civil Engineering Infrastructure. We also provide site videos, estimation tutorials, and interview preparation content. Let's move ahead. Now let us understand the vehicle damage factor, VDF. This is very important. VDF represents how many standard axles worth of damage a single commercial vehicle causes. A standard axle is defined as an 80 kN, 8.16 tons, single axle with dual wheels. Indicative VDF values as per IRC 37-2018 are: plain rolling terrain 0 to 150 CVPD 1.5, 150 to 1500 CVPD 3.5, more than 1500 CVPD 4.5. Hilly terrain 0 to 150 CVPD 0.5, 150 to 1500 CVPD 1.5, more than 1500 CVPD 2.5. But friends, these are only indicative values. If you want a precise and accurate design, you should conduct an axle load survey at a weighbridge. Weigh all truck axles for at least 24 hours and then calculate the actual VDF from the collected data. This will give the most accurate value for your specific project. The concept is based on the fourth power law: the heavier the axle, the greater the damage. If the axle load doubles, the pavement damage increases 16 times. So remember, heavier loads mean exponentially higher damage. Now let's move to the foundation, subgrade characterization. The life of a road largely depends on the strength of the subgrade. The most common test used to measure subgrade strength is the California Bearing Ratio (CBR) test. In the CBR test, a 50 mm diameter plunger is used. It penetrates the soil at a rate of 1.25 mm per minute. The resistance offered by the soil is compared with that of standard crushed stone aggregate. The result is expressed as a percentage, %. Now, how do we calculate the resilient modulus, MR, from CBR? If CBR less than or equal to 5% is equal to 10 times, MR is equal to 10 times CBR in MPa. If CBR greater than 5% is equal to 17.6 times 0.64, MR is equal to 17.6 times CBR. 0.64 in MPa. Minimum requirements. Subgrade CBR should be at least 8%. If CBR is less than 2%, the soil should be replaced or stabilized. Always consider the effective CBR based on the worst moisture condition of the year when the soil is at its weakest due to maximum water content. Friends, so far we have understood traffic and subgrade. Next, we will move towards pavement layers. This video is long but extremely valuable. Watch it completely to get full clarity of all concepts. And yes, if you have any doubts, ask in the comments, we will definitely reply. Don't forget to subscribe to Civil Engineering Infrastructure. Now let us look at the typical layer composition of a flexible pavement from bottom to top. Layer 1, subgrade, natural soil. CBR greater than or equal to 8%. Resilient modulus, MR, calculated from CBR. This is the bottommost layer and acts as the foundation. Layer 2, subbase course, GSB, granular subbase. Thickness, 150 to 500 mm. CBR greater than or equal to 20%. Grading as per MORTH specifications. Function, load distribution and drainage. Layer 3, base course. Options. WMM, wet mix macadam, most commonly used. CTB, cement treated base, when higher strength is required. Crushed stone base. Thickness, 100 to 300 mm. Layer 4 bituminous layers. DBM, dense bituminous macadam, intermediate layer, 50 to 150 mm. BC, bituminous concrete, wearing coarse, 25 to 50 mm, topmost layer. Overall, a typical pavement section could be 500 mm GSB plus 250 mm WMM plus 100 mm DBM plus 40 mm BC is equal to 890 mm total pavement thickness. This configuration may vary depending on traffic and subgrade strength, but this gives a clear understanding of how layers are arranged in a flexible pavement system. Now let us discuss the properties of granular layers in detail. Granular subbase, GSB. Resilient modulus is equal to 0.2 times 0.45 times MR is equal to 0.2 times H. 0.45 times E. Subgrade, where H is equal to thickness in mm and S subgrade is equal to subgrade modulus. Poisson's ratio 0.35. Minimum CBR 20%. Grading 75 mm to 0.075 mm as per MORTH table 400-1. Wet mix macadam WMN. Resilient modulus 300 to 450 MPa. Poisson's ratio 0.35. Aggregate impact value less than 30%. Grading 53 mm to 0.075 mm. Binder, stone dust or lime is used. Crushed stone base. Resilient modulus 400 to 600 MPa. CBR greater than 80%. Strong angular aggregates. Important, the main function of granular layers is to distribute the load so that less pressure reaches the subgrade. Therefore, their thickness and material quality play a very important role in pavement performance. Now it's time to discuss the bituminous layers, the topmost part of the pavement that directly faces traffic and weather conditions. Dense bituminous macadam, DBM. Binder content 3.5–4.5% bitumen. Air voids 3–5% after compaction. Resilient modulus at 35 degrees Celsius, 1500 to 2500 MPa. Thickness 50 to 150 mm. Function provides structural strength and load-bearing capacity. Bituminous concrete BC. Binder content 5.0–6.0%, higher bitumen content because it is the wearing coarse. Air voids 3–5%. Resilient modulus at 35 degrees Celsius, 2000 to 3500 MPa. Thickness 25 to 50 mm. Function provides a smooth riding surface, skid resistance, and waterproofing. Temperature effects. In hot weather, the bituminous layer becomes softer and its modulus decreases. The standard design temperature for most parts of India is 35 degrees Celsius. In cold areas, softer grade bitumen such as VG10 or VG20 is used. In hot areas, harder grades like VG40 or polymer modified bitumen PMB are preferred. Important, the quality of bitumen and its temperature susceptibility play a major role in determining the pavement's service life. Now let us discuss some special layers that are used on high-traffic roads. Cement treated base CTB. Cement content 3–4%. 7-day unconfined compressive strength UCS 4.5 to 7.0 MPa. Resilient modulus 5000 to 8000 MPa, very stiff. Used when traffic is very heavy, greater than 30 MSA. Cement treated subbase CTSB. Cement content to 3%. 7-day UCS 1.5 to 3.0 MPa. Less stiff than CTB, but stronger than granular layers. Warning sign: critical warning. Whenever CTB or CTSB is used, a crack relief layer must be provided above it. Cement-treated layers develop shrinkage cracks, and these cracks can reflect into the upper bituminous layers, leading to premature failure. Crack relief layer options. SAMI, stress-absorbing membrane interlayer 10 to 20 mm thick. 40 mm asphalt concrete, AC with modified binder. Geosynthetics, polymer grids or geotextiles. Note: CTB CTSB should be designed as structural layers, but providing a crack relief layer is mandatory to control reflection cracking. Friends, so far we have understood all the layers and materials. Now comes the most interesting part: IITPAVE software. This is the tool that helps you perform the actual pavement design. It is extremely useful for site engineers. Watch the video completely, and if you want a detailed video on any specific topic, let us know in the comments. Don't forget to subscribe to Civil Engineering Infrastructure. Now let us come to the main topic. IITPAVE software. This is our primary design tool. IITPAVE was developed by IIT Delhi under research scheme R56. It is based on multi-layer elastic theory. It is distributed along with the IRC 37018 code and is available free of cost. There is no license fee required. System requirements are simple. Java runtime environment must be installed. It runs on Windows 7, 8, 10, and 11. Minimum 2 GB RAM is required. The interface is simple and does not require a high-end graphics card. Installation is easy. Download it from the IRC or MoRTH website. Install Java. Run the setup file and you are ready to use it. IITPAVE can analyze up to 10 pavement layers. It supports single wheel and dual wheel loading. It allows analysis at multiple points. It provides output values for stress, strain, and deflection. This software was jointly developed by IIT Delhi and Banaras Hindu University specifically for Indian conditions. Now let us see how to enter data in IITPAVE step by step. Layer data for each layer. Thickness, H in mm, for example 150 mm, 200 mm. Elastic modulus, E in MPa, for example 500 MPa, 2000 MPa. Poisson's ratio, mu usually 0.35 for granular layers and 0.25 to 0.35 for bituminous layers. Loading data. Wheel load, standard 40 kN single wheel, for an 80 kN axle. Tire pressure, 0.56 MPa, single wheel, or 0.8 MPa, dual wheel. Contact radius, A automatically calculated by the software. Dual wheel spacing, 310 mm, standard value. Analysis points, where to check. Rutting check, at the top of subgrade, vertical compressive strain. Fatigue check, at the bottom of each bituminous layer, horizontal tensile strain. Radial distances, 0 mm, center, 150 mm, 200 mm, etc. Coordinate system. Z-axis, vertical direction, downward positive. R-axis, radial distance from the load center. Origin, load center at the pavement surface. Friends, is the software interface clear now? Next, we will look at the actual design procedure, how to select a trial section, how to check it, and how to redesign if required. This is the most practical part. Share this video with your juniors and colleagues. and subscribe to Civil Engineering Infrastructure so we can bring you more software tutorials. Now let us understand the complete design procedure in 5 steps. Step 1. Data collection. Conduct a traffic survey, determine CBPD, growth rate, and vehicle composition. Perform subgrade testing, obtain CBR values and soil classification. Conduct an axle load survey, determine the actual VDF from weighbridge data. Step 2. Calculate design traffic, MSA. Use the formula. N is equal to 365 times A times D times F times 1 plus R N 1 R, where A is equal to initial CBPD, D is equal to lane distribution factor, F is equal to vehicle damage factor, VDF. The result gives N in million standard axles, MSA. Step 3. Select trial section. Estimate initial thickness based on experience or IRC design charts. Decide material types, GSB, WMM, DBM, BC. Select layer thicknesses, for example, 200 mm GSB plus 150 mm WMM plus 80 mm DBM plus 40 mm BC. Step 4. Determine material properties. Assign elastic modulus, E, and Poisson's ratio, mu, for each layer. Calculate subgrade MR from CBR value. Select modulus of bituminous layers based on design temperature. Step 5. IITPAVE analysis. Enter all data into the software. Run the analysis. Obtain critical strain values for fatigue and rutting checks. This is the systematic approach for designing flexible pavements as per IRC 37-2018. Now comes the most important part, how to perform the design checks. Check 1. Fatigue cracking for bituminous layers. Allowable tensile strain, epsilon T, allowable, formula. For 90% reliability, less than or equal to 2.21 times 10 4 times 1 0.854 times 1 0.854 epsilon T less than or equal to 2.21 times 10 4 times 1 MSA 0.854 times 1 MR 0.854 for 80% reliability. Different constants are used as per IRC provisions. Check 2. Rutting for subgrade. Allowable compressive strain, epsilon Z, allowable, formula. For 90% reliability, less than or equal to 1.25 times 10 3 times 1 0.854 epsilon Z less than or equal to 1.25 times 10 3 times 1 MSA 0.854 for 80% reliability, less than or equal to 1.75 times 10 3 times 1 0.854 epsilon Z less than or equal to 1.75 times 10 3 times 1 MSA 0.854. Validation. If computed strain less than or equal to allowable strain, design is safe. If computed strain, allowable strain redesign is required. How to redesign? Increase thickness of bituminous layers to control fatigue. Increase thickness of granular layers to control rutting. Use better materials with higher modulus. Rerun IITPAVE and check again. This is a trial and error process. and you continue refining the section until both fatigue and rutting criteria are satisfied. Now let us discuss the design charts. These are useful when software is not available. In IRC 37-2018, several design charts are provided. Chart 1, Granular Base with Bituminous Surfacing for CBR 2%. Chart 2, Granular Base with Bituminous Surfacing for CBR 5%. Chart 3, Cement Treated Base with Bituminous Surfacing. Chart 4, Pavements with Subbase CBR 20% and 30%. How to read the chart? X-axis, Cumulative Standard Axles, MSA, plotted on a logarithmic scale. Y-axis, Total Pavement Thickness, mm. Curves represent different subgrade CBR values, 2%, 3%, 5%, 7%, 10%. Steps to use the chart. Locate your calculated MSA on the x-axis. Move vertically upward until you intersect the curve corresponding to your subgrade CBR. From that point, move horizontally to the left to read the required thickness on the y-axis. The value obtained is the total pavement thickness, measured from the top of the bituminous layer down to the top of the subgrade. Limitation. Design charts are meant only for preliminary estimates. The final design should always be validated using IITPAVE because the charts do not cover all possible material combinations and design conditions. Now let us go through a complete worked example, applying everything step by step. Given data. Road, National Highway, 4-lane divided. Initial traffic, a 2000 CVPD, commercial vehicles per day. Growth rate, R5% is equal to 0.05. Design life, N 15 years. Lane distribution factor, D 0.45, for 4-lane divided road. Vehicle damage factor, F 4.5, heavy traffic. Subgrade CBR, 6%. Step 1, Design Traffic, MSA. N is equal to 365 times 2000 times 0.45 times 4.5 times 0.05, 1.05, 15.1. N is equal to 365 times 2000 times 0.45 times 4.5 times 21.58. N is equal to 31.8 MSA. Step 2, Subgrade Resilient Modulus, MR. MR is equal to 17.6 times 6, 0.64. MR is equal to 58.6 MPa. Step 3, Proposed Pavement Section. BC, 40 mm, E is equal to 3000 MPa. DBM, 100 mm, E is equal to 2000 MPa. WMM, 250 mm, E is equal to 450 MPa. GSB, 200 mm, E is equal to 250 MPa. Step 4, IITPAVE check. Computed epsilon T is equal to 120 microstrain. Allowable epsilon T is equal to 150 microstrain, OK. Computed epsilon Z is equal to 280 microstrain. Allowable epsilon Z is equal to 350 microstrain, OK. Result. The design is safe. Friends, did you understand the example? This is exactly the same process used in real highway projects. Now only the last 2 slides remain, special considerations and final summary. Stay till the end of the video, because in the summary we will revise all the important points. And if you want more technical videos like this, subscribe to Civil Engineering Infrastructure and press the bell icon. Now let us discuss some special considerations that are very important in the field. Drainage. Provide a cross slope of 2.5-3% to prevent water stagnation. Side drains are mandatory, especially in high rainfall areas. Protect the subgrade from water. Proper waterproofing and drainage are essential. Construction quality. Achieve 98% of MDD, modified Proctor density, during compaction. Bitumen temperature 140-160 degrees C during laying and 90-100 degrees C during rolling. Carefully check the quality of longitudinal and transverse joints. Climate factors. High rainfall areas such as Konkan and Northeast increase bitumen content by about 0.5%. High temperature areas such as Rajasthan and Gujarat use VG 40 grade bitumen. Cold areas such as Himachal and Kashmir use softer grades like VG 10 or polymer modified bitumen PMB. Freeze-thaw regions provide a special frost protection layer. Maintenance. Apply surface dressing every 3 to 4 years. Seal cracks as soon as they appear. Repair potholes immediately to prevent larger failures. Important, design is crucial, but construction quality and maintenance are equally important for achieving the full service life of the pavement. Final slide, summary and key takeaways. IRC 37-2018 highlights. Mechanistic empirical approach, scientific and accurate design method. IITPAVE software, free tool based on multilayer elastic analysis. To failure criteria. Fatigue, tensile strain. Rutting, compressive strain. Design traffic, minimum to MSA, if less, use IRC SP 72. Reliability levels. 90% for national highways and expressways. 80% for state highways and major district roads. Remember the design process. Calculate traffic MSA. Test subgrade CBR MR. Select a trial section. Analyze using IITPAVE. Check computed strains against allowable values. If not safe, redesign. Advantages. Optimal thickness, neither excessive nor insufficient. Cost-effective design. Better performance prediction. Scientific validation. Friends, road design is both an art and a science. IRC 37-2018 provides the scientific foundation, but field experience is equally important. Always consider local conditions, material availability, and construction capability while designing. Thank you very much. And yes, if you found this video helpful, please like the video. Share it with your friends. Subscribe to Civil Engineering Infrastructure. Comment your suggestions and doubts. See you in the next video. Until then, Jai Hind.